Hello everyone. In this video, we will introduce our latest research work, titled Fast Time Varying Formation for Discrete-Time Multi-Agent System with Retroactive Memory, Theory and Experiments. In previous studies, to improve the convergence speed of multi-agent systems during time-varying formation, researchers have often focused on increasing the algebraic connectivity of the communication topology, thereby achieving faster convergence through explicit data-driven approaches. In fact, existing studies have shown that the convergence speed of time-varying formation can also be improved by exploiting the historical information of each agent and its neighbors. In other words, retroactive memory enables the effective use of historical data and provides an implicit acceleration mechanism. In this study, we investigate the time-varying formation control problem for second-order discrete-time multi-agent systems. We propose a discrete time formation tracking protocol with retroactive memory, referred to as ARM-FC. Moreover, we derive the analytical form of the optimal control law for the low-order memory case. Finally, for the high-order memory case, we develop an optimization algorithm that can improve the convergence rate of the closed-loop system. In this video, 16 sets of physical simulation experiments and 16 sets of indoor flight experiments are fully recorded, allowing viewers to intuitively observe the performance of the proposed method when applied to quadrotor UAVs. Specifically, we conducted the feasibility verification experiment, universal validation experiment, and comparative experiment to comprehensively evaluate the proposed method. The feasibility verification experiment includes 3 experimental groups with different memory orders. The universal validation experiment includes experimental groups with different communication topologies, numbers of nodes, and formation configurations. The comparative experiment includes 4 experimental groups. In the physical simulation experiments, we conducted 16 sets of verification experiments using the QStudio platform. In the indoor flight experiments, the key components mainly include the QDrone 2 UAV platform, the OptiTrack motion capture system, and the workstation. First, we present the feasibility verification experiment. The experiment currently shown on the screen is F3, which is the baseline experimental group with a memory order of 3. The lower left panel shows the physical simulation process, while the curves at the bottom present the 6 degree of freedom states of the UAVs. The right and upper right panels show the top view perspectives of the UAVs during the flight experiment. Next, we present the experimental processes under 3 different memory orders in the feasibility verification experiment. The first, second, and third rows show the experiments with memory orders of 0, 1, and 3, respectively. Second, we present the universal validation experiment, and shows the flight experiments in the universal validation experiment under different communication topologies, numbers of nodes, and formation configurations. These experiments are presented in the first, second, and third rows, respectively. Finally, we present the comparative experiment. The screen shows the performance of 4 different methods during the flight experiments. C1 corresponds to the proposed method in this paper, namely ARM-FC. C2 and C3 adopt formation control methods of the same type as the proposed method, driven by position data and acceleration data, respectively. C4 is a formation control method based on an event-triggered mechanism. The main contributions of this study are summarized as follows. First, we propose a control protocol that exploits retroactive memory information to accelerate the convergence rate of time-varying formation for second-order discrete-time multi-agent systems. Second, we provide the analytical optimal control law for low-order memory cases, and develop a convergence-accelerating optimization algorithm for high-order memory cases. This enables the closed-loop system to achieve a high convergence rate even under low algebraic connectivity. Finally, both physical virtual simulations and flight experiments are conducted to verify the effectiveness of the proposed method in time-varying formation control of multiple UAV systems.